Have you ever wondered about the ripples in the fabric of space-time? Now that's a question that's been intriguing scientists and philosophers alike for centuries. To understand these ripples, let's first take a step back and consider space-time itself. Space-time, in its simplest definition, is the four-dimensional fabric of our universe. It's a seamless blend of the three dimensions of space we're familiar with, length, width, and height, with the single dimension of time. Think of it as a giant cosmic quilt, stretching infinitely in all directions. Now, this quilt isn't just a passive backdrop against which the universe's drama unfolds. No, it's a dynamic, interactive part of the cosmos. Picture a bowling ball on a trampoline. The weight of the ball causes the trampoline to warp or curve around it. This is similar to how massive objects like stars and planets distort the fabric of space-time. Their mass causes space-time to curve around them, creating a gravitational field. Objects moving within this field will follow the curvature of space-time, which we perceive as gravity. Imagine an apple falling from a tree. It's not that gravity is pulling the apple down. Rather, the apple is following the curve of space-time created by Earth's mass. It's a subtle shift in perspective, but it fundamentally changes how we view the universe. So we've got this four-dimensional cosmic quilt that's being continually distorted by the mass and motion of celestial bodies. But what happens when something really massive moves abruptly? Picture two black holes spiraling towards each other, or a star exploding in a supernova. These cataclysmic events cause space-time to not just curve, but ripple. These ripples propagating at the speed of light are what we call gravitational waves. They're like the cosmic equivalent of ripples spreading across a pond after a stone is thrown into it, but on a scale that's mind-bogglingly vast and incredibly minute at the same time. So what happens when something really massive moves abruptly? It creates what we call gravitational waves. Imagine two black holes orbiting each other at incredible speeds. This is where we begin our journey into the birth of gravitational waves. These cosmic giants, each potentially millions of times heavier than our sun, dance a deadly duet, spiraling closer and closer together. As they orbit, they spin faster and faster, reaching speeds that are almost incomprehensible to the human mind. The energy in this cosmic ballet is immense, rivaling the output of billions of stars. Now, if we pause for a moment and think about the fabric of the universe, we can begin to understand how this energy creates something utterly fascinating. You see, according to Einstein's general theory of relativity, massive objects like black holes distort the space-time around them. It's like a heavy ball on a rubber sheet, causing it to dip and curve. So, when these black holes spin around each other, they don't just move through space-time, they twist and churn it. This creates waves, much like the ripples you see when you toss a stone into a pond. But unlike those water ripples, these waves are disturbances in the very fabric of the universe itself, spreading out at the speed of light. Now, let's take this a notch higher. Imagine the moment when these twirling black holes finally merge. The energy released in that single moment is astronomical, literally. It's equivalent to converting several suns entirely into energy, following Einstein's famous equation, E equals mc squared. This colossal energy shakes the universe, causing space-time to ripple and shudder. These ripples spread out across the cosmos, stretching and squeezing space-time as they go. They pass through stars, galaxies, and eventually, billions of light years later, they might even pass through us here on Earth. These ripples, these disturbances in space-time, are what we call gravitational waves. They are whispers from the distant universe, giving us unparalleled insights into the most violent and mysterious events in the cosmos. Detecting these gravitational waves is no easy task. Imagine trying to spot a single grain of sand in the vast expanse of the Sahara Desert. That's essentially what scientists are up against when they try to detect these ripples in space-time. Gravitational waves are incredibly elusive. They interact very weakly with matter, making them exceptionally difficult to detect. At this point, you might be asking, if these waves are so elusive, how can we possibly detect them? Well, that's where some of the most advanced scientific instruments come into play, interferometers. These devices are capable of measuring incredibly tiny changes in distance, changes so small that they are thousands of times smaller than the nucleus of an atom. Interferometers work by splitting a beam of light into two. These beams then travel along two separate paths, bounce off mirrors, and recombine. If the length of the paths changes due to a passing gravitational wave, the beams will no longer perfectly cancel each other out when they recombine. This results in a change in the light intensity, which can be detected and measured. But even with this ingenious method, detecting gravitational waves is still a colossal challenge. The signals are so faint, and the disturbances they cause are so minute, that it's like trying to measure a distance change equivalent to the thickness of a human hair over a distance comparable to the stretch from us to the nearest star, Proxima Centauri. To make matters more difficult, there are numerous sources of noise that can mimic or mask the signal of a gravitational wave. Everything from seismic activity to thermal noise to quantum fluctuations can interfere with the detection of these elusive waves. But despite these seemingly insurmountable challenges, scientists have persevered. They've developed incredibly sensitive instruments, refined their techniques, and have even built multiple interferometers around the world to cross-check their findings. It took us over a century and some of the most sensitive instruments ever built to finally detect these waves. In 2015, a faint chirp heard around the world changed our understanding of the universe. This wasn't just any chirp, mind you. It was the long-awaited sound of two black holes over 1 billion light-years away, spiraling into each other and merging into a single entity. This cosmic dance produced ripples in the fabric of space-time, gravitational waves that traveled across the cosmos to reach our humble planet. This was the first detection of gravitational waves. It was achieved by an observatory so sensitive it could detect changes smaller than 1,000th the diameter of a proton. This observatory is known as LIGO, the Laser Interferometer Gravitational Wave Observatory. Located in two parts of the United States, LIGO is a giant L-shaped device that uses lasers to measure minute distortions in space-time caused by passing gravitational waves. The first detection was no easy feat. It involved countless hours of meticulous data analysis and verification. Imagine the thrill and trepidation of the LIGO team when they first spotted the signature of a gravitational wave in their data. It was like finding a needle in a cosmic haystack. But they had done it. They had detected the undetectable. This discovery was nothing short of revolutionary. It confirmed a key prediction of Albert Einstein's general theory of relativity and opened up a whole new way to study the universe. The scientific community was abuzz with excitement. Theoretical predictions were becoming observable facts. The cosmos was no longer silent. It was humming with gravitational melodies waiting to be heard. The first detection of gravitational waves marked a pivotal moment in human history. It was a testament to our relentless pursuit of knowledge and our insatiable curiosity about the cosmos. It was a message from the universe, reminding us of the wonders that lie beyond our blue marble. The discovery was so groundbreaking it earned the 2017 Nobel Prize in Physics. This was a well-deserved recognition of a truly extraordinary achievement, and it was just the beginning. The era of gravitational wave astronomy had dawned, promising to unravel the mysteries of the universe in ways we could hardly imagine.
So we've detected gravitational waves. What does that actually mean for us? These are ripples in space-time, much like the ripples you see when you drop a pebble into a pond. And these waves are generated by the most violent events in the cosmos. Black hole mergers, neutron star collisions, and supernova explosions. But these aren't just interesting cities, they have profound impact for our understanding of the universe. First, gravity will give us a completely new way universe. Until now, our knowledge of the cosmos has been based primarily on light, from radio waves to gamma rays. But light can be blocked or distorted by dust, gas, and other objects in its path. Gravitational waves, on the other hand, pass through everything undisturbed, giving us a clear view of that produces them. Second, waves give us new insights into the nature of black holes and neutron stars. For example, by studying the gravitational waves produced by a black hole merger,
determine the masses and spins of the involved. This can help us understand how these exotic objects form and evolve over time. Third, gravitational waves could also help us solve some of the biggest mysteries in physics. For instance, they could shed light on the nature of dark matter, the invisible stuff that makes up about 8% of the universe's matter, are eluded direct detection. By studying the gravitational waves produced by events involving dark matter, we might finally get a handle on what this mysterious substance of. In short, the gravitational waves is a game changer for astrophysics. It's like we've been given a new set of eyes, allowing us to see the universe in a way we never could before. And who knows what other cosmic secrets these ripples in space-time will reveal. Gravitational waves open up an entirely new way to observe and understand our universe.
We're just at the dawn of gravitational wave astronomy. Imagine standing on the shores of a vast cosmic ocean, its waters filled not with fish, but with ripples of space-time. These ripples, known as gravitational waves, are the aftermath of cataclysmic cosmic events, black hole mergers, neutron star collisions, and perhaps even the Big Bang itself. So, what does the future hold for gravitational wave astronomy? Well, in the coming decades, we can expect to see significant advancements in detection technology. Today's detectors, such as the Laser Interferometer Gravitational Wave Observatory, or LIGO, are already incredibly sensitive, able to detect gravitational waves from billions of light-years away. But future detectors will be even more so, allowing us to probe deeper into the universe and detect more subtle waves. These technological advancements will not only increase our ability to detect gravitational waves, but also our understanding of them. We'll be able to study their properties in greater detail, such as their speed, polarization, and frequency. This will provide us with new insights into the nature of gravity and the behavior of space-time. But perhaps the most exciting aspect of gravitational wave astronomy is the potential for new discoveries. Just as the advent of radio astronomy opened up a new window into the universe, so too will gravitational wave astronomy. It will allow us to observe phenomena that are invisible to traditional telescopes, such as the interiors of black holes and the very early universe. These discoveries could revolutionize our understanding of the universe. They might confirm existing theories, such as Einstein's general relativity, or challenge them, leading to the development of new theories. They could also shed light on some of the universe's greatest mysteries, such as the nature of dark matter and dark energy. In conclusion, the future of gravitational wave astronomy is bright and filled with promise. It's a thrilling time to be involved in this field as we stand on the brink of a new era of discovery. Who knows what secrets of the universe these ripples in space-time will reveal to us in the future? It's a fascinating time to be alive, isn't it? We've journeyed through the cosmos, delving into the birth, detection, and implications of gravitational waves. We've unraveled the whispers of the cosmos, the ripples in space-time caused by cataclysmic cosmic events such as black hole mergers and neutron star collisions. These gravitational waves, once thought to be undetectable, have not only been detected, but have also begun to reshape our understanding of the universe and its evolution. Each detection is a milestone, a testament to human curiosity and innovation. The discovery of gravitational waves is akin to receiving a new sense, a new way of perceiving the universe. It opens up a whole new realm of astrophysics, offering us unprecedented insights into the most violent phenomena in the cosmos. As we continue to explore the universe's mysteries, remember, every ripple in space-time is a whisper from the cosmos, telling us its stories. In the grand scheme of the cosmos, we're all learners, aren't we? If you found this journey through space-time intriguing, if you learned something new from this video, then please give it a like and share your thoughts in the comments below. Your feedback helps us to create more content that sparks curiosity. Now imagine your friends, family, or anyone you know who loves to learn. Wouldn't they enjoy this journey through the cosmos as well? Share this video with them, and let's spread the knowledge. Let's ignite the curiosity in others too. And if you haven't already, do consider subscribing to our channel. We've got plenty more journeys to embark on, plenty more cosmic whispers to unravel. You wouldn't want to miss out, would you? So hit that subscribe button and join us as we continue to explore the mysteries of the universe. Remember, every ripple in space-time is a whisper from the cosmos, telling us its stories. So let's keep listening, let's keep learning. Don't forget to subscribe and share. Until next time, keep looking up.